Welcome to this special edition of Frequency Matters, the RF and microwave update series. I'm Pat Hindle, and I'm here with my special guest, Ethan Lin, Vice President at TMY Technology, located in Taiwan. Welcome, Ethan.
Hi, Patrick. That's my honor to join your interview section.
TMYTEK is a group of Taiwanese high-frequency engineers whose designs range from active components to front-end systems for millimeter wave applications such as 5G and SATCOM. Ethan, TMYTEK is a relatively new company. Can you tell me about how you got started and some of your technical background?
Yeah, sure. Thank you for asking. That's a very good question because millimeter wave technology it's not a super hot topic before 5G. So I will review a little bit back to the background of my team. Actually, the image I showed up here is the black hole image. That's what taken in last year, in 2019. An image was taken by a millimeter wave telescope. So that's millimeter wave in astronomy. And actually, to have the very first black hole image in the human being history, Taiwan really contributed 3 of 8 telescopes. And they are all in millimeter wave and sub-millimeter wave band. Especially this one, sub-millimeter wave array, located in Hawaii, in Mauna Kea. So Academia Sinicon Institute of Astronomy and Astrophysics, that's where we are from, actually. So the founder and myself, the co-founder, we are Sui and myself, we are all from Institute of Astronomy and Astrophysics. Sui is, his expertise is in millimeter wave system and components, cryogenic engineering, and MMIC design. My background is more in embedded system design, software, and system integration. So that's how I work with the Sui. We can build up the whole team to apply millimeter wave technology to 5G new radio.
Can you tell us how you are enabling easy and fast 5G prototyping with your products?
For 5G new radio millimeter wave, the key feature of the new radio millimeter wave is phase array and the beamforming technology. So actually, when we start up the company, we observe what's the pain points and what kind of problem hasn't been resolved yet in the market. And we found there are 3. And that's why we map our technology to concur, to overcome each specific topics one by one. The first one is Pat, you introduced, we developed a very good R&D tool to help people to do faster prototyping. Because there's no R&D tool for beamforming or especially for millimeter wave band in the market. So we built up the tool. That's our first solution. We call it B-Box. I will show you later. The second problem we found from the market is if millimeter wave really need to enable a massive deployment, the traditional OTA testing will be too slow. And that's the second topic we try to resolve. The solution maps to that issue. We call it XBeam. And the third one, we found a phase array is essential. And antenna package, AIP, is the most elegant and the right solution to address phase array manufacturing and design. So I think that's all 3 topics. And to answer this specific question, how we help people to speed up the prototyping by B-Box. That's the B-Box tool. Here I'm going to show you very quickly. Actually, that's how B-Box looks like. We build up everything from antenna to front-end module, but we separate the antenna and the front-end circuit separately. We do it intentionally because we want to provide the flexibility of the design. For example, people can design the array antenna, the golden plate part, separately. and click the antenna back to the system. So with one system, they can try out maybe 10, even 100 different millimeter wave antenna design. So this really helped to reduce the cost of your R&D process.
Yeah, I've seen this in person. It's very impressive. It's easy. You just clip on the antenna and it works. So what type of technologies do you use to enable beamforming and antenna connection that's so easy?
Here, as you can see from the picture, we use SMPM connector here. There are 16 4x4 SMPM connector array. So actually here, we use some kind of, the loss here is higher than AIP. But what we gained from the design here is the flexibility. So a little bit path loss here through the connector, but we have great flexibility for antenna designer.
How do you see companies enabling low-cost, high-throughput 5G OTA testing in production?
That's our XBeam solution. Before I get into the solution here, I'd like to show you the traditional how people is doing OTA testing. Traditionally, a mechanical-based positioner and chamber was always needed for OTA testing. That's essential for R&D process because we need to learn how the phase array works. Then we need to measure the pattern, the radiation patterns, right? But obviously for production environment, that's very slow because that's mechanical positioner based. That's the first issue. The second issue is it's very bulky. The size is kind of big. It's kind of quite good to fit into production line. And the third issue is that's not very easy to do the automatic integration with the production line. So to improve that part, actually we create a XBeam technology. In this technology, essentially we remove all mechanical parts. We only use our beamforming box with a beam steering based technology to measure or to characterize the DUT. So the main purpose is that we create a new methodology for OTA testing. Actually, we don't really care the whole patterns. We care about what really need to be known in the production line. For example, the power, that's one thing for sure, and people need to know the power of the main beam. And also we need to know the beam steering angle. Is the beam switching angle is correct or not? Probably that's the most essential question where we need to know in production line. And the key feature is that's very fast. In production line, we have no time to measure one module or one smartphone with a couple of minutes, or we need to do it in 10 seconds or in 30 seconds. So we create the technology XBeam is really help to speed up the OTA testing.
So you mentioned antenna and package technology. Why is that needed for millimeter wave 5G and LEO markets?
So traditionally, actually from 1G to 4G LTE, the carrier frequency is relatively low. We always use sub 6 gigahertz. And in sub 6 gigahertz, a long cable and a connector-based antenna is affordable because the path loss of the signal is not to impact to the transmission. For example, in the left part of the diagram, there's the iPhone, there's iPhone mainboard and iPhone antenna module. There's Wi-Fi and a cellular module in one module. As you can see here, even Apple uses a long cable and a connector-based antenna module because it's sub 6. So a long cable is affordable. But in millimeter wave, the path loss is very high. So there's no way to separate antenna to circuit too far away. In this case, the only implementation or the only feasible implementation is to bring antenna very close to IC. Just like what I showed here in the right side, there are two diagrams here. Let's look at the bottom one. In the surface here, there's some patch antenna, and in the bottom, there's RFIC and BGA leads. So that's why AIP is essential technology for 5G millimeter wave.
What types of packaging are you developing to meet the needs of 5G O-RAN products?
The packaging type here is more relevant to the processing technology. We use PCB-based technology. We also use ceramic-based technology. We call it LTCC. It's low temperature co-firing ceramic. And in Taiwan, there's also one advantage. We have very good connection to the most largest packaging house in the world who do the packaging for TSMC. So we have 3 different types of packaging technology we can use for our AIP. Like I mentioned, we have various technology in Taiwan we can available to TMYTEK. So actually, we already implement quite a few AIP projects with very top companies in the world. In this slide, I show you 3 examples where we work with other companies. The most left one is 1x8 AIP. That's the antenna in package. We work with the 3rd largest antenna company in China. They design antenna itself, and we do the package design and implement. But for that one, it's designed for UE. For the middle part, that's an 8x8 AIP. In this case, we already incorporated with up-down converter. So the output of the module is IF ready. We also can tile up the 8x8 AIP to form a larger array. Like the background image shows that there are 4 8x8. So effectively, that's 16x16. And the most right part is a very good example. We work with a very top Japan LTCC company. We implement a 4x4 LTCC AIP. Still the same, we can also form a larger array by tiling up the stuff together. So I think at TMYTEK, we are focused on 5G millimeter wave technology and AIP technology. We hope we can contribute to the world with our technology and our services.
Ethan, thank you very much for joining me today and providing insight into TMY technology. We appreciate you taking the time to meet with us. And we thank everybody for listening to us, and keep in tune with Frequency Matters.